Good afternoon. Welcome to my talk towards Lockfree persistent homology. My name is Arnur Nigmetov. This is joint work with Dmitriy Morozov, and we both work in topological data analysis. The main idea of this field is to describe the shape of data using tools provided by algebraic topology, and there are many applications of topological data analysis, perhaps most notably in neuroscience and in material science. And in almost all of these applications, the descriptor which is used is a so-called persistence diagram. The goal of our project is to parallelize the computation of its descriptor. So just to give you an idea of how it looks like, let's consider this example. A persistence diagram is always a set of points in plane. In this case, it corresponds to this synthetic data set, also planar. There are points sampled from two circles of different radius, and these two topological features, these two holes, will be captured by these 2 points in the persistence diagram. It will also contain some topological noise closer to the diagonal y equals x, but I don't have time to talk about this. I'll just say that essentially computing a persistence diagram is just some special form of Gaussian elimination. We work over Z2, the field with 2 elements, and the matrix that we are working with is called the boundary matrix. It is a large, sparse matrix with entries 0 and 1. And our goal is to reduce it. Let's make it a bit more precise. Low of I will denote the index of the lowest non-zero entry in column I of the matrix D, so the lowest one. And we say that there is a collision between columns I and J if their lowest non-zero entries are in the same row. That is, if low of I equals low of J. And the matrix is reduced if there are no collisions. How can we eliminate a collision? We add one column to another, and we always add from left to right. And in this case, 1 plus 1 equals 0. So this 1 disappears, and we eliminated this particular collision. A nice property is that any sequence of such column addition operations will lead us to the same persistence diagram, the correct persistence diagram. Maybe the reduced matrix will look differently depending on which choices we made, but the persistence diagram will be restored uniquely, correctly. And this allows us to implement a conceptually straightforward parallelization algorithm. We just split the matrix D into chunks of some fixed size. We create a pool of threads, and each thread reduces a column in its chunk from left to right. When it's done, it takes the next available chunk, and so on. We maintain a lookup table of pivots, that is, the columns which are used to kill the lowest ones in the columns to the right from them, the columns that we add to other columns. And we use atomic variables and compare and swap primitive to avoid locks in our chunk reduction function. The atomicity of pivots ensures the correctness of our algorithm. And there's another ingredient which I must mention, memory reclamation. It turns out that when a thread is done with a certain column, it cannot immediately release the memory taken by its previous version, because maybe some other thread needs access to the non-reduced version of the same column. On the other hand, we cannot defer freeing all the memory until we are done with the whole reduction process, because the matrix is large. And we use the memory reclamation technique based on quiescent states. This quiescent state happens when a thread is done reducing one chunk, and then it can release the versions of columns which are guaranteed to be unnecessary, so no thread needs them. We made some experiments to see the scaling and to compare with the alternative. It is the alternative because there's only one shared memory parallel implementation of computing persistence diagrams. It's called PHAT. It uses an algebraic approach, not this inherent parallelism that we are using. And Also, there are many sequential implementations of persistence homology, which use different optimizations, and our approach can be combined with almost every optimization in these sequential implementations. To demonstrate this, we also parallelized the state-of-the-art software for computing one specific type of persistence diagrams, so-called Vitoris Rips persistence homology, and this software is called Ripser. So let's take a look at PHAT experiments. Here, the number of threads and the running time are in log scale, and our algorithm is in blue. So you can see that it scales rather well, and it outperforms PHAT starting from 5 threads. There are 2 different settings, 2 different modes in which PHAT can operate. So for this setting, it outperforms it right away from 2 threads. Now let's take a look at Ripser. Here, a single-threaded version necessarily runs slower. I mean, our parallelized version has some overhead, but this overhead is negligible. The scaling, however, is also satisfactory, and we see some significant speed up to 10 threads. We measured this speed up on different inputs for the parallelized Ripser, and the speed up factors differ from input to input, but as the number of threads remains moderate, say below 10, there is always some significant acceleration. So to sum up, we implemented a shared memory parallel algorithm for computing persistent homology. Our algorithm typically demonstrates good scaling behavior if the number of threads is not too large. It can be combined with many other optimizations, and we demonstrated it by integrating it into Ripser. So here I stop, and thank you for your attention.